Previously, we've explored Jupiter and some of its moons through the lens of the electromagnetic spectrum, which you can see in this video here. Today, we will be revisiting this approach, but this time, rather than a planet, it'll be adapted to investigate a highly energetic ball of plasma. The light we'll be looking at is old. Although light is the fastest thing we know, the image of the sun that we see from Earth is approximately 8 minutes and 20 seconds old, meaning we are viewing what the sun looked like a few minutes in the past. And if you count how long it takes the photons generated within the sun's core to make their way through each layer of the sun before escaping into space, the light that reaches us is anywhere from 10,000 to 170,000 years old. Where to begin? Like eating a fruit by starting with the outer layers and working your way in, let's start our investigation with the outermost layer of the sun's atmosphere, the corona. The following image was taken by the Solar Dynamics Observatory, or SDO, a NASA space mission launched back in February 2010. SDO aimed to better understand the solar variations that influence life on Earth and our technological systems by studying the dynamic solar surface and atmosphere at different electromagnetic wavelengths. By looking at light beyond the visible range, NASA was able to pick out normally invisible details crucial to our understanding of the sun. This image was taken using a 19.3 nanometer wavelength, representing light found in the extreme ultraviolet region. At a wavelength corresponding to a color temperature of 1 million Kelvin, we can clearly see the higher region of the sun's corona. Interestingly, the sun's corona can also be seen by the naked eye on rare occasions, such as during a total solar eclipse. When the moon is perfectly aligned between the Earth and the sun for a fleeting period of time, the view of the central, brighter disk, known as the photosphere, is fully blocked, revealing a radiant exterior. While this is a breathtaking view already, the corona is still nowhere near as detailed as it is in this image taken by the SDO. This makes it a useful tool for scientists' studies. But let's go a little deeper, to features of the sun just beneath the corona. At a color temperature of 20 million Kelvin, the intensely vivid spots indicate events known as solar flares. Here is some footage of a particularly busy week for flares back in August 2022. I've always found solar flares to be both terrifying and hypnotizing. They are colossal explosions where the sun spews out an immense amount of electromagnetic radiation. They are caused when magnetic fields cross, distort, and reorganize themselves rapidly. This activity is created by the turbulent nature of the plasma within the sun itself, from which the fields ultimately originate. But they are not the only feature of the sun's atmosphere venting radiation. Coronal holes, indicated here by this darker region on the sun, are another fascinating feature which we'll take a closer look at using extreme ultraviolet light. Coronal holes are areas of cooler, less dense plasma which are magnetically open, meaning that rather than forming closed loops that go back to the sun's surface, the field lines travel outward across the solar system. These areas allow solar wind particles to escape more easily into space. When these solar winds are directed towards and collide with Earth's magnetosphere, beautiful auroral lights dance across the night sky at the Earth's polar regions. Using ultraviolet light gives us a much better view of these fascinating features of the sun's outer layers. Non-visible spectrum light is an incredible tool, and there are so many different features in the sun's outer layers to look at. There are solar filaments, known as solar prominences, the large loops of plasma that rise from the sun's surface. These enormous loops are large enough to make the Earth look like a tiny speck and can stretch hundreds of thousands of kilometers into space. They can form in as little time as a day, but a stable prominence can remain in the corona for several months. In this example, we watch as a solar prominence snakes its way out of the photosphere and into the sun's atmosphere. Although this video is sped up so the minutes seem like seconds, when you consider the size of the prominence, it becomes clear how swiftly the sun's intense magnetic fields are causing this material to move. One fact you might not know about the sun's atmosphere is that it sometimes rains there. Not all of the charged plasma fired into the sun's corona continues out across the solar system. Some remains in the corona, getting trapped and cooled until it falls back to the sun's surface as a shining rain. This coronal rain is beautiful to look at, but is best observed from a distance. It's still millions of degrees in temperature. Of course, falling gently back to the sun's surface is only the fate of some of the sun's plasma. This is where the comparison to Earth fails. After all, on Earth, the clouds do not crack like a released elastic band firing into space. On the sun, thanks to tightly wound magnetic fields, they do. This is a time-lapse of a coronal mass ejection. Watch as the structure forms at the bottom left of the sun for some time, before eventually snapping and sending billions of tons of plasma out across the solar system. Even with the Earth's magnetic field, being hit by a powerful one of these could be devastating for our satellites and electrical grids. All these structures are imaged by the SDO here utilizing a 30 nanometer wavelength of light, which corresponds to the extreme ultraviolet portion of the electromagnetic spectrum. Timing is important when trying to image these features, as they are more common in certain years than in others. In fact, each structure is dependent on the solar activity of the sun, alternating around an 11-year solar cycle, which I did a video about here. But there's more to learn. Just as using visible and ultraviolet light shows us different things when looking at the same feature, using two different wavelengths of non-visible light can also be eye-opening. To demonstrate this, take a look at these two images of the sun's corona. Taken over the same time period, the following two images use different wavelengths of light. The first, imaged at a color temperature of 600,000 Kelvin, depicts the quiet corona and features coronal loops. The second, imaged at a color temperature of 2 million Kelvin, displays the much hotter active regions of the corona. The stark comparison between the two images highlights the importance of using different approaches when investigating the star. What may initially appear to be a singular solar phenomenon can be revealed as a complex, intertwined chain of events, and we still haven't technically made it through the sun's atmosphere yet. Moving further inwards, let's look at another image produced by the SDO utilizing a 160 nanometer wavelength of light, this time of the transition region. The transition region is a layer which sits between the sun's corona and the chromosphere, the lowest layer of the sun's atmosphere. It's a very shallow layer, approximately 100 kilometers in thickness. In this region, the thermal temperature of the sun rises dramatically from around 8,000 to 500,000 Kelvin. For an earthly comparison, fiercely scalding lava erupting in Hawaii is 1,170 degrees Celsius or 1,443 Kelvin. The temperature at the lower, deeper end of the transition region is almost 6 times hotter than this. At the upper end of the transition region, the temperature is more than 346 times hotter. Traveling even deeper, we find ourselves immersed in the sun's chromosphere, which is the last layer of atmosphere before we reach the sun's surface itself. Imaged here, using 170 nanometer ultraviolet light, it is estimated to be approximately 1,700 kilometers thick. Closely inspecting the chromosphere, we identify some mesmerizing features known as spicules. Swaying like long, wavy grass blowing in the wind, these long jets of plasma shoot upwards from the sun's surface at speeds up to 100 kilometers per second, approximately 282 times faster than the speed of sound, and can reach lengths of nearly 10 kilometers, over 1 kilometer taller than Mount Everest. Forming and vanishing in around 5 to 10 minutes on average, the processes behind these spicules were widely unknown and debated for some time, as it wasn't clear how magnetically charged particles could ever escape the sun's magnetic fields at that level. That is, until 2017, when a team of scientists working on an extremely detailed model of the spicules discovered that their origins must be related to neutral particles. Scientists had not originally included neutral particles in their models of the sun, as they didn't think they affected the motion of the magnetically charged particles. But once they were added, it transpired that the neutral particles gave the magnetically charged particles unexpected buoyancy they needed to escape the sun's plasma and shoot up into spicules. Descending further through the sun's lower atmosphere, we eventually reach the photosphere, the surface of the sun itself, which is best imaged using visible light. While the edge of the photosphere appears sharp and precise, as it often does to our naked eye, this is simply due to how far away the sun is. The sun itself is not solid at all. Since it is too hot for matter to exist in a solid, liquid, or gas state in any region of the sun, it can only be plasma, referred to as the fourth state of matter, and is estimated to make up 99.9% of all the matter in the universe. Plasmas tend to behave a lot like gases, except they are made up of a mixture of ionized atoms and free electrons. The photosphere is the outermost layer in this image, around 400 kilometers thick. It is not a fixed, solid boundary of the sun, unlike what this image may suggest. And sadly, it is the deepest layer of the star which scientists can measure directly. At a closer look, you may notice some dark spots on the left-hand side. These are known as sunspots and appear darker than other parts of the photosphere due to their cooler temperatures. But that's only in comparison to their scorching hot surroundings. Unlike coronal holes, sunspots form in areas where magnetic fields are particularly powerful. Here, heat becomes trapped beneath the photosphere due to decreased convection within these areas. When comparing this image of the sun to a previous one taken using extreme ultraviolet light over the same period, a connection between sunspots and solar flares emerges. The captivating solar flares and sunspots coincide at the same location. From peering beneath the surface, it becomes clear that one must lead to the other. Now let's take a closer look at some similar sunspots. This image was taken using the Swedish Solar Telescope, based here on Earth, and using a wavelength of visible light of approximately 400 nanometers. Next to and surrounding the sunspots, the photosphere is saturated with these jagged-edged, endlessly shape-shifting cells, which doesn't look dissimilar to lava as it cools and cracks. However, these cells are around 1,000 kilometers wide and are known as solar granules. Consider them from the top layer of a churning convection cell underneath. Brighter areas inside each granule represent fluid of unimaginable temperatures rising from within the sun's upper interior layer to its surface. Upon reaching this boundary, the fluid has nowhere to go except to spread outwards and across. After cooling gradually, the fluid sinks back inwards via the rough, dark boundaries surrounding each cell before repeating the cycle. This process closely resembles the convection currents within the Earth's mantle, responsible for driving plate tectonics. This process is no joke. While on average it is estimated that each granule lasts for as little as 20 minutes, the flow within the cells reaches supersonic speeds of more than 7 kilometers per second, generating waves on the sun's surface due to sonic booms. Fascinatingly, these granules can also be seen in the full disk view we saw earlier, utilizing the same wavelength of visible light. You may think this image looks quite grainy for such a high-tech space probe, and you're right, it does. But that graininess is the granules on the photosphere of the sun. not a processing effect or excess noise in the image. And that's it. Sadly, our journey ends here, as scientists have not yet figured out how to image deeper into the sun, using either visible or non-visible light. Much of what lies beyond this layer remains shrouded in mystery. But we can see the benefits of using light of all different spectrums in our study of the sun. They help us observe exploding solar flares, vast coronal holes, swaying spicules, intriguing sunspots, and shape-shifting cells, just to name a few, in completely new ways. The sun is abuzz with lively activity, and so much of it would be invisible to us were it not for these imaging techniques. Maybe one day we'll find ways to see deeper, using techniques we can barely dream of currently, just like those ancient generations of humans long ago could hardly dream of the methods we're utilizing these days. But for now, just knowing there is so much going on unseen in the universe, and knowing we have the means to uncover it, fills me with excitement and curiosity. Who knows what else might be out there, waiting to be found. If I were to tell you that the cycles of the sun could affect your entire life, you might think that I was suddenly taking a turn away from astronomy and into astrology. While there are many people in the world who believe that you can learn things about your future by studying the position of stars and planets, it's not a position I tend to take on this channel. I'm more interested in the beauty of space and the mechanisms that explain why it is the way it is. But sometimes there is a grain of truth behind even the most surprising of stories. So allow me to put on my prophesying hat. While I'm no writer of horoscopes, I will predict that based on the current state of the sun, over the next few years, you might be more likely to experience bad health, less reliable technology, see warmer weather with fewer clouds, and possibly could be influenced in other surprising ways. How do I know? Because it turns out the sun, that giant ball of fire in our sky, is not just the place we get our energy from. Science is starting to show that its 11-year cycles might just be the metronome measuring out how life on our planet tick, tick, ticks. I'm Alex McColgan, and you're watching Astrum. Today we're going to look at sun cycles. In particular, I intend to show you exactly how the cycles of the sun are already influencing the course of your life. It's no surprise that the sun is influential to life on Earth. After all, in many respects, it is life's origin. Life on Earth needs energy to function, and the sun frequently provides that energy. Light for plants, plants for herbivores, herbivores for carnivores, all the way up the food chain. It's hard to find anything on Earth that could live without our sun. But beyond the gift of that life-sustaining energy, it's easy to think of the sun as fairly static. We see it rise and fall in the sky, but we rarely notice it undergoing any sort of change. This, however, is an illusion. The sun changes all the time. As science has advanced and we've been able to shield out the worst of the sun's glare, it became possible to study the sun's surface. As early as 1610, it became clear that the sun was a boiling, shifting sea of barely restrained plasma, which frequently wasn't restrained. In spite of the intense gravitational force holding it all together, the nuclear reactions taking place in its core are so hot, reaching 15 million degrees Celsius in its center, that plasma bubbles and bursts on its surface, erupting into solar flares that blaze in all directions. Sunspots, dark patches of the sun's surface that are filled with intense magnetic fields and can be between 1,600 and 160,000 kilometers across, form, drift, and vanish. Coronal mass ejections explode out of the sun's corona, the atmospheric zone above the sun that is strangely 200 times hotter than its surface. It's hard to find a place in the solar system that is as active as the sun. What many people do not realize is that that activity waxes and wanes. The Sun operates on an 11-year cycle that alternates between a period of low activity, the solar minimum, to a much higher level, the solar maximum, and then back again. Sunspots, solar flares, and CMEs all become more common during the solar maximum. You are 50 times more likely to see a solar flare during solar maximum compared to the Sun's minimum, and large CMEs go from happening once every few days to multiple times in a single day. This is known as the Schwabe cycle. Interestingly, this represents 1/2 of a larger cycle known as the Hale cycle, which maps the changes in the Sun's magnetic polarity. Once every Schwabe cycle, every 11 years, the Sun's magnetic north pole and south poles swap places. When another Schwabe cycle occurs, the poles swap back. Tick, tick, tick. This constant rising and falling of solar energy levels thrums through our planetary system, rising and falling like a heartbeat. And surprisingly, even though we can't see it, we here on Earth move to its rhythm. We don't really understand why the Sun goes through this cycle. It's clearly related to the magnetic processes that exist within the Sun itself. Yet, although we have observed these cycles in action for the last 200 years and have seen evidence of their influence on the Earth over the last 10,000, we're still no closer to figuring out why the Sun cycle has a length of that particular time period rather than any other. What force drives it? Lacking any other obvious answer, some scientists have tried to connect the orbital length of Jupiter, also about 11 years, to this cycle length, but this could easily be a coincidence. Although Jupiter represents 2.5 times the combined mass of all the other planets in the solar system, and definitely exerts some gravitational pull on the Sun, its orbit cannot explain the variations, seemingly random, that the Sun's cycle undergoes. Much of what goes on within the Sun is a mystery to us, but its influence on Earth, that is much easier to see. It begins with the space around us. Space is more and more important to modern civilization, so it shouldn't be surprising that CMEs and solar storms streaming out from the Sun more regularly would have an impact on the technology we have up there. Scientists are able to predict the arrival of a solar storm, known as a geomagnetic storm, by the time it arrives at Earth, days or even weeks in advance. This allows astronauts to go into safe shelters to hide themselves from harmful rises in radiation levels, and it also allows the delicate hardware on satellites to be powered down to prevent that hardware from being fried. This is important, as solar radiation can cause unexpected electrical currents to form in wiring, overloading systems that haven't gone into a safe standby mode. But there's another aspect to geomagnetic storms that you might not expect. All of that radiation has an impact on the atmosphere itself. It warms it, albeit just a little. As the atmosphere warms, it expands, and this has an impact on our satellites. In space, there is no drag, so objects can orbit practically forever. Well, this isn't entirely true, and satellites in low Earth orbit do occasionally, about 4 times a year, need to expend fuel to correct their orbits, as there is still a tiny amount of atmosphere up there. But when a geomagnetic storm occurs, the atmosphere blossoms upwards, and low Earth orbit satellites have to maneuver every 2 to 3 weeks to keep from falling from the sudden friction. And this isn't always enough. In 1989, there was a geomagnetic storm that was so powerful it knocked the NASA Solar Maximum mission out of the sky, as an increase in atmosphere suddenly slowed the satellite down. Ironically, the mission had been studying solar flares. This is not an isolated incident. NORAD, the Northern American Aerospace Defense Command, has to relocate hundreds of satellites after each geomagnetic storm, as they have been knocked out of their old orbits. Radiation can also influence our ionosphere, filling it with charged plasma. This can have a slight lensing effect on your GPS systems, reducing their accuracy from within a meter to over 10 meters. The next time you look on Google Maps and it thinks you might be a street across from where you are, a geomagnetic storm might be to blame. Our power grids brace themselves every 11 years for the uptick in these current-inducing events to keep themselves from being overloaded. Amateur radio enthusiasts and airline pilots find their high-frequency radio range dropping significantly as radio waves get deflected or even blocked completely by the more powerfully charged ionosphere. As I predicted in my horoscope, this all adds up to some less reliable technology. The fact that the next solar maximum is expected to arrive soon, in 2025, makes me quite confident in my prophesying. There are some bright sides to this. As space weather becomes more turbulent, parts of the world such as Canada see a rise in the number of auroras dancing hypnotically across the sky. Aurora chasers report rises in sightings from a few times a year to as many as twice a month during the most energetic parts of the sun's 11-year cycle. So much for the sun's influence on space and our technology. You might think that that's the end of it. The sun cycle might influence machinery, but it's not going to make much difference on anything alive, right? If you think that, you'd be wrong. It's not for nothing that the rest of my horoscope mentioned poorer health. There's growing evidence that the sun cycles can even influence ecosystems and species themselves, including humans. Some of this is incidental. When the Schwabe cycle is at the solar minimum, the sun exerts less pressure through its solar winds, which means, ironically, that we get less protection from our heliosphere from cosmic radiation. This form of radiation is highly energetic, but fortunately rarely makes it through our atmosphere for that very reason, as it's likely to be absorbed or deflected by a passing air molecule. But reaching the atmosphere is all that's needed to produce an effect. There is a theory, although still far from certain, that this extra radiation could be creating nucleation sites in the atmosphere that seed extra clouds, influencing our weather. Even if that's not occurring, during solar maximum, the space weather hitting our atmosphere can raise global temperatures slightly. As my horoscope at the beginning predicted, a warming of the weather. Not by much, it should be said, less than half a degree, and the temperature always eventually returns to where it started, but it's enough that it's noticeable to species paying attention to temperature, for instance to decide when to start the mating season. Studies of birds have shown that on warmer years they tend to lay eggs earlier. Curiously, a study published in 2009 by researchers in the Netherlands went as far as to show that the laying times of blue tits were also affected by the number of sunspots occurring, which even the researchers found hard to explain. It's not like birds can look at the sun to see how many sunspots there are. Nevertheless, a link seems to exist, according to the 5 nesting groups that were looked at. This isn't something that affects just blue tits, or even species like homing pigeons that are sensitive to magnetic fluctuations, who fly different routes depending on what time in the 11-year cycle it is. I'm talking about the last unmentioned point in my horoscope, bad health. There are numerous studies on how solar cycles might influence us. In 2011, a study spanning 2 decades of nearly 1/3 of women in Holland discovered a peak in 6 cervical pathologies that took place just after solar maximum, when the sun's radiation was hitting hardest. The study also checked 1 man during the same period, which admittedly is a much smaller number of candidates. Still, it was interesting to note that the man experienced slight elevations in oral temperature, pulse rate, blood pressure, and respiration rate that took place soon after solar maximum too. It's not just physical. There's even an influence on the rate of mental disorders. A study in 2006 looked at 237,000 clients in the main Medicaid database collected between 1995 and 2004. They found that, of all those clients, those born during higher energy chaotic cycles experienced an increased rate in mental disorders. If this is the case, then the cycle of the sun at the moment of your birth might just have influenced the course of your life. It's not quite star signs, but astrology might just be onto something. at least with one specific star. Ultimately, the science on this is still ongoing, and it should be stressed that any health impacts caused by these cycles are extremely minor. As one researcher put it, it took hundreds of thousands of patients to even notice that there was a health impact. The sun cycle should not prevent you from living your life. We're currently heading towards a solar maximum, predicted to arrive in 2025. But for those who are worried, living through or being born in a solar maximum isn't all bad. The same study suggested that this radiation might lead to a rise in creativity and adaptability. Perhaps it was during one such cycle, 80,000 years ago, that a human brain was mutated to give it abstract thought and consciousness. If so, if they gave us the means to perceive the universe, we have much to thank solar maximums for. We wouldn't be us without them. What does the sun sound like? It's a simple enough question, and one that comes with a simple enough answer. The sun is silent, of course. Because sound doesn't travel in a vacuum, to us, the sun sounds like nothing at all. But let's do away with simple answers. What if sound actually could propagate through space? Without a giant cosmic muffler between us and our closest star, what would we hear? Would the sun sing to us, an enchanting melody in our sky? Or would its noise be such a cataclysmic cacophony, it would instantly be the last thing we ever heard? Scientists actually have the answer. Through spacecraft like the Parker Probe, which is currently making skimming orbits around the sun, they can detect the kind of pressure waves and particles emitted by the sun and can convert those waves into the sounds we might hear if space was capable of such propagation. And interestingly enough, not all of the sun's sounds are the same. I'm Alex McColgan, and you're watching Astrum. Join with me today as we listen to several different sounds made by the sun, recreated through clever science, because it turns out that these sounds may allow scientists to solve two of the sun's greatest mysteries. In our imaginary scenario, where space has suddenly gained the ability to propagate sound, we can now start listening to the sun all the way from Earth. Although the Earth is 152 million kilometers away from the sun on average, it's perhaps unsurprising to learn that the sun is very loud, easily audible from where we are. It would sound something like this. Just a reminder, there is no sound in space. This is a sound reconstruction, turning amplitudes and frequencies into sound waves, creating clips of what the waves might sound like to the human ear if an atmosphere were present. This soothing buzz has an almost electrical feel to it. It reminds me of generators, or perhaps even something vaguely radioactive, which is appropriate given that this is the sun we're talking about. The nuclear fusion going on inside the sun is equal to 3.85 times 10 to the power 26 watts every second. About 1 million times more than what humanity produces in an entire year. All of this power being created has an unsurprising knock-on effect on the volume of the sound the sun would produce. To get a sense of what this would be like, take the device that you're watching this on and connect it up to the speakers that they use at your next rock concert. Then play this noise at full blast. At 110 decibels, this volume level is survivable for short periods of time, but would likely end up with the entire population of the planet going deaf if they weren't wearing earplugs as it plays in our sky non-stop. In fact, we can consider it extremely fortunate that we don't actually have to deal with this. Species would have probably evolved with no ears, as hearing would be pointless. If we get closer to the surface of the sun, that sound level grows exponentially, with some experts rating it at 270 decibels. Remember, decibels are a logarithmic scale, so every 10 decibels higher it goes, you have to multiply the sound level by 10. To get a sense of how loud this would be, 270 decibels is louder than our atmosphere itself can physically convey. There is a cap on sound at 190 decibels in Earth's atmosphere, as different mediums have different volume caps, due to some complicated quirks of wave amplitude and energy levels, which we won't go into here. The volume of the Sun would be 100 million times higher than this cap. The Sun is loud. Which is a shame, as some of the Sun's sounds can only be differentiated when we enter that ear-splitting zone. By the time the noise of the Sun has reached us, many of the Sun's sounds have blurred into one, meaning we miss out on some of their fascinating intricacies. To gain a better insight into the Sun, we would need to get closer, entering into that blisteringly loud zone of noise. So let's ignore the volume of the Sun for now, and instead let's focus on its sound patterns. If we were to enter a spacecraft and head towards the Sun, we would soon begin to hear a difference in the sound's uniformity. Rather than a constant buzzing, we would hear something like this. This is the sound of the solar wind. The Sun emits a constant stream of charged particles that blasts out across the solar system, and its existence represents one of the Sun's greatest enigmas to date. You see, it's tempting to think of this stream from starting inside the Sun and blasting outward under the incredible force of all that nuclear fusion. However, by the 1960s, an important discovery had been made through observation. Although particles within the Sun's atmosphere, or corona, were moving around with an average speed of 145 meters per second, particles outside of the corona were traveling at 618 meters per second. This meant that particles that had enough speed to escape from the Sun's surface were drifting into space, and then something in the Sun's corona was hyper-accelerating them from subsonic to supersonic speeds, firing them off. What kind of process or mechanism is doing this remains a mystery to this day. The corona contains a second enigma too. It is far too hot. Although you might expect the center of the Sun to be the warmest part of it, and the temperature to gradually go down the further from the center you go, this stops being true once you enter the corona. The surface of the Sun has an average temperature of 5,600 degrees Celsius, but within a few kilometers, the corona suddenly sees the temperature jump to as high as 2 million degrees Celsius. Something in the Sun's corona is flicking solar wind into space, and something is making things very hot. Scientists do not know why this is happening either, although it is thought to have something to do with magnetic fields. It's here that we would meet the third sound of our tour of the Sun. As our spaceship would draw closer and we passed over the boundary between the corona and empty space, something known in science as the Alfvén surface, we would begin to hear the following. These are known as Langmuir waves. They are formed by tiny oscillations of plasma particles vibrated by light itself as they stream from the Sun through tiny funnels on the Sun's surface, a magnetic equivalent to the sound a kettle makes when it boils. We have entered one such stream. Countless of these streams fire out from the Sun's surface. The Sun's exterior is covered in islands of hot material rising from the star's center. Once there, the material cools and sinks back into the star's mass along the island's edges, and something about this process of rising and falling material, or something going on within the Sun itself, makes these sinking zones stream out powerful magnetic field lines. Plasma is scooped up by the magnetic force and is sent streaming into space, the starting point of the solar wind. Scientists don't know what causes this process, but the sound of Langmuir waves is eerily beautiful. As the winds head out, not all the waves created in this way travel at the same speed. This has the effect of spreading out sounds, as faster parts of the wave run ahead while slower parts of the wave fall behind, creating what are known as dispersive waves. Such waves are filled with chirps, little eddies of sound where fast waves coming from behind meet slow waves already traveling ahead. Eventually, this evens out into the hum we heard at the beginning. There is one last sound that might offer an insight into the entire mystery, one that has some intriguing implications. Here, right within the sun's boiling corona, we can finally begin to detect Whistler mode waves. Whistler waves are the distant echo of high-energy events that ring through the plasma of a celestial body's magnetosphere. We get them on Earth. Whenever lightning cracks, you get more than just thunder. A ripple travels through the planet's magnetosphere that can be picked up kilometers away if you have the right detectors. To truly get a sense of the scale of these waves, here is what they sound like on Earth. Just a few small little cracks and whistles, nothing too special. Now, here's what they sound like on the Sun. To go from sparse, brief clicks to a cacophony of wailing wind indicates that the Sun's magnetosphere is not just experiencing the odd crack of lightning. Something is going on constantly, all over, merging individual moments together into one incessant roar. Scientists are still trying to figure out what that roar is being caused by, but at least one theory for the force behind this sound, which can account for the dramatic acceleration and superheating of matter within the corona, is a dry-sounding little event called magnetic reconnection. Magnetic reconnection sounds fairly innocuous, and yet its innocent, technical-sounding name disguises a cataclysm. The Sun is a tensely wound-up ball of shifting magnetic field lines, all due to that churning plasma within its heart. I cannot stress enough how powerful these are. When magnetic field lines travel away from the Sun, it's sometimes possible for them to merge with other field lines, causing some of those iconic loops to form that you've likely seen in images of the Sun before. However, at the moment such arcs are formed, all hell breaks loose. When two parallel lines touch, creating an arc, there's a massive realignment in the excess field line's polarity. Everything above the arc needs to find a place to go to ensure magnetic equilibrium is maintained. Cut from their tethers, the field lines further out from the Sun form an arc of their own, which then catapults off into space like the releasing of a gargantuan stretched rubber band. This rapidly accelerating magnetic force is known as a nanoflare, and it indirectly heats the corona above it to multi-millions of degrees in seconds. Scientists have only recently developed the capability to be able to even see nanoflares, and aren't entirely certain the nanoflares they've seen are indeed the hypothesized events they were expecting, although they do seem to be accompanied by the expected superheating. This is an explanation that is still being worked out. Most of it is not yet understood. And still, it's not completely far-fetched that such moments when the Sun gets so wound up it snaps explain why its corona is as hot as it is, and why it is flinging solar winds out across the solar system with quite the force we witness. Although, to go from a single crack into the roaring wail that we hear, and to account for the constant solar wind travelling outwards in all directions from the Sun, nanoflares, or whatever the force behind this phenomenon is, must be extremely widespread throughout the entire corona. The Sun continues to hold many mysteries. The Parker Solar Probe, which collected many of these sounds, continues its journey around the Sun, gathering valuable data with every pass. The Parker Probe is only 4 years into its 7-year mission, so hopefully it will collect plenty more information for scientists to pore over. Perhaps they will find more sounds for us, each one a clue to the ancient riddle of how the universe works. Because ironically, just like listening to the ticking of a clock to try and figure out how the clockwork functions, the secrets to the Sun might one day be solved by what we hear rather than by what we see. It is something hardwired into humans to want to be remembered. For thousands of years of mankind's history, people have erected monuments to themselves and performed great deeds, all to endure after they'd passed on. It's no wonder some people might want to be the one who made a great scientific discovery, like discovering a special star or a planet, so they'll be remembered for all time. However, being overzealous could lead to being remembered for all the wrong reasons. I'm Alex McColgan and you're watching Astrum, and in today's video we're going to be looking at the fascinating discovery of a planet in our solar system closer to the Sun than Mercury. It was observed dozens of times by various astronomers. The only problem? It doesn't actually exist. Let's rewind to the year 1846, when something astounding had just happened in the scientific community. Aubin Jean-Joseph Le Verrier, a French astronomer and mathematician, had just helped discover the planet Neptune using nothing but pure mathematics. He had been examining the rotation of the then 7 planets when he noticed that something was off about Uranus. It didn't seem to be moving in line with the theories of gravity proposed by Newtonian physics. Le Verrier reasoned that the only explanation for this was that there must be a planet out beyond the orbit of Uranus that was perturbing its motion to account for this discrepancy. He did some maths and then declared that his 8th planet must exist at an exact point in the night sky. The incredible thing was, after hearing his prediction, Le Verrier's friend Johann Gottfried Galle got out a telescope, searched in that location, and sure enough discovered the planet Neptune in a single hour. It was almost exactly where Le Verrier had predicted that it would be. The scientific community went wild with this discovery, and Le Verrier was rightly celebrated for his incredible deductions. So it's not surprising that a decade later, when he predicted the location of a 9th planet using the same methodology, the scientific community listened. In fairness, he had not been the first to predict that such a planet existed. It was as far back as 1601 that German astronomer Christoph Scheiner had claimed to have noticed a strange black spot moving in front of the Sun, and had claimed that this was a planet. In reality, it was most probably a sunspot. Other alleged sightings had been made throughout the years. Capelle Loft in 1818, Franz von Greuthuysen in 1819, J.W. Pastorff between 1822 and 1837 all claimed to have seen an object or objects orbiting the Sun. Pastorff claimed to have seen it at least 12 different times. People had even begun to spitball a name for this hypothetical planet. In 1846, French astronomer Jacques Babinet suggested calling it Vulcan, after the Roman god of volcanoes, fire and metalwork. This would have been an appropriate name, as any planet closer to the Sun than Mercury would have been exceptionally hot. Mercury already experienced temperatures of 427 degrees Celsius. Vulcan would have been even hotter. And yet, for all these sightings, confirmation of the planet remained elusive. But what made Le Verrier's claim stand out was the way he had come to make it. In 1845, before his discovery of Neptune, Le Verrier had been asked by the director of the Paris Observatory to apply Newton's laws of physics to the orbit of the planet Mercury, to see if the two lined up. Le Verrier did so, laying out a theoretical orbit that Mercury would take around the Sun based on Newtonian physics. Once his prediction was made, astronomers observed Mercury to see how well it matched up. Only it did not. Le Verrier tried again. Reasoning that it was possible his maths had been out, he did a much more thorough study in 1859. Using multiple observed sightings of Mercury as his baseline, he once again mapped out Mercury's orbit. But once again, his predictions were out. Not by much, only 45 arcseconds per century, but enough that there was conclusively something weird going on. Confident of his maths this time, Le Verrier reached the conclusion that there must be some mass pulling Mercury out from the idealized orbit, either a planet or a series of asteroids. Given his success by now at locating Neptune, many astronomers believed him. Scientists rushed to telescopes to try and spot the alleged planet, and it wasn't long before results began to come in. Spotting a planet so close to the Sun was inherently difficult. The glare of the Sun would completely obliterate the reflected shine of a tiny planet, As such, the most effective method of spotting such an object was to see the darkening it caused as it travelled across the Sun. And in 1859, Edmond Modeste Lescarbot claimed to have seen just that. Lescarbot was a French amateur astronomer and physician who, using basic tools in a homemade observatory, claimed to have spotted a small black object passing by the Sun on the 22nd of December. He wrote to Leverrier, who was so taken by his claim that he travelled by train to the man's home unannounced to verify it. He questioned Lescarbot, heard his observations, and came to the conclusion that the man was telling the truth. So the two of them announced to the scientific community Lescarbot's discovery. They named the planet Vulcan. The scientific community was once again very impressed. Lescarbot was given the Légion d'honneur, the highest order of merit in France. He got to speak at meetings of learned scholars. There was only one problem. The planet he had discovered didn't actually exist. There were numerous proofs of this. For one, naturally, other scientists wanted to take a look at this new planet Vulcan. Leverrier calculated from Lescarbot's observations that Vulcan must orbit 21 million kilometers out from the Sun and did so every 19 days and 17 hours. So it would be easy to spot, as it would be calculable when it would pass the Sun again next. Astronomers pointed their telescopes towards the Sun at the appointed time, but Vulcan was a no-show. Leverrier was troubled by this, but by then more reports were coming in of the planet's sighting. Other astronomers were going back through their records and were matching up phenomena they had seen with the new planet Vulcan. Some of these were years out of date and not even listed as to when in the year they had happened, but Leverrier still used these to tinker with his model, reasoning that perhaps his maths were just out. So he would predict and would not see Vulcan, and would rework his theory and would not see it again. Another piece of damning proof came from Emmanuel Liais, another French astronomer. Liais claimed that he had been coincidentally looking at the Sun at the exact moment Lescarbot had, with a twice as powerful telescope, and had not seen the planet Lescarbot had claimed to have observed. Vulcan's existence floated through murky waters, as there were renowned scientists who did claim to see it from time to time. Leverrier died in 1877, but just a year later in 1878, two well-renowned astronomers both claimed to have seen Vulcan at the same point in the sky at the same time during a solar eclipse. They even both claimed that the planet was reddish in color. The corroboration was compelling, yet Vulcan still did not exist. In science, if a fact is true, then it is repeatable. And in spite of all these observations throughout the years, Vulcan was never repeatably observed. It was never seen during a solar eclipse again. In time, that corroborated sighting was put down to calculation errors and misidentifying a known star. But ultimately, the one who finally put the idea of Vulcan to rest was Albert Einstein, and he did so by thinking of something completely different. Numerous scientists over the years had attempted to see Leverrier's planet Vulcan because mathematically they were certain it had to exist. Newtonian physics demanded that it did. They strained to see it, and in that confirmation bias, they did see it again and again, just never in the same place. But Einstein realized that it was Newtonian physics that was at fault. In 1915, he proposed a model of physics that accurately described the motion of the universe, but relied on things like curvature of space-time rather than gravity. At slow speeds, it looked a lot like Newtonian physics, but when you placed objects like Mercury next to very massive objects like the Sun, special relativity predicted a different path for their orbits. And sure enough, Einstein's model predicted the exact orbit that Mercury made around the Sun, deviations and all. And with that, the case for Vulcan's existence evaporated. Under special relativity, it couldn't exist. There could be no object next to the Sun of a planetary size, or it would mess with Mercury's orbit so that it would no longer line up with the maths. And this time, Einstein was able to prove his maths correct through tests like the Eddington experiment. There is a lesson in this somewhere. Sometimes if we want something too much, we find it regardless of whether it is really there or not. Sometimes it takes thinking outside the box and challenging our previously held beliefs before the truth can be found out. As scientists, and equally as lay people, it's important that we do not hold too tightly to our ideas. The truth does not need our fervour. It will prove itself given time and opportunities for repetition. So there you have it. The planet Vulcan, a planet of fire that was nothing but smoke and mirrors, a yearning for something but never a reality. Newtonian physics were replaced by Einstein's theories of relativity, and now special relativity is here to stay, at least until it is supplanted by something even more comprehensive too. Have you ever looked up at the sky and seen something so strange it made you wonder if you were dreaming? Perhaps you saw what looked like a rainbow, only it was upside down. Or maybe you saw a perfect circle of light around the sun with 2 splashes of rainbow color on the sides. Well, no need to pinch yourself. What you are seeing is a unique category of optical phenomena called ice halos. Although similar, they aren't technically rainbows, but their own distinct wonder. Some are relatively common, while others are extremely rare. As you might know, rainbows occur when sunlight is refracted by water droplets suspended in the atmosphere. When light travels from one transparent substance to another, such as from air to water, its speed changes, bending its path and separating the light into colored bands by wavelength, a process called dispersion. But what happens when light hits water particles that are made of ice rather than liquid water? Well, depending on the shape and orientation of the ice crystals, as well as the direction of the light hitting them, they can produce a whole range of optical phenomena. To date, 119 kinds of ice halos have been categorized, and there might still be others we don't know about. So what are ice halos? How do they form? And what should you look for if you want to see one for yourself? And finally, are they a sign of something more ominous on the horizon?